Okay, last night I got some good results, and I took everything apart and put it all back together this morning, and I got the exact same thing, which is good. So I get the very low draw when I short out the curved shunt bar windings. There's 3 ohms here, 3 ohms here. You know, and it goes from the top of this secondary diagonally down and enters the bottom of the opposite secondary. That's the way the core goes of the steel florist wire. It's about 1/2 inch, 3/8 of inch thick core inside here. And it goes from here to here. And it does the same thing on the other side, from here to here. Okay, without these windings on there, it doesn't work very good. But when I do these windings and I short them out, it works really good. And I think these windings being shorted out create like maximum current in there when it's induced by the back EMF flowing through there. This is my guess, and it really sucks all the back EMF from one secondary to the other, bypassing the primary the way a bit is supposed to work. So this like enhances and makes stronger the back EMF flow through that core, the shunt core. So that's what I think is going on. So you see right now I have 8.3 volts and 10 milliamps. It's jumping around. Only 10 milliamps here. I'm going to lower it just a bit. Anyways, 8.3, 10 milliamps, even though it's jumping up to 2 now. And across this 30 UF cap is 6.4 volts, and the amps to the cap from the secondary is 40 milliamps. And here's the load I have across the cap is 15 ohm inductive load, which is the secondary of this, or the primary, whatever it is. The high voltage side of the transformer is the load across the cap, 15 ohms worth. So it comes to 0.083 watts in and 0.256 watts out. And I also did some tests at 20 volts instead of 8. And now I have 1.6 watts in and 2.94 watts out. So it's about doubled. But this is tripled here when you go down to 8.3 watts. I mean 8.3 volts. It's a triple. And I also did 11.3, and it's about double you get out compared to in. And now out is apparent power through an inductive load. Okay. Amps in is a watts in. I would say it's pretty stable what it says. And because we're working in 60 hertz AC, everything's in AC. If this was in like, 500 hertz or something, and I was using these meters, you wouldn't be able to trust it. But because it's 60 hertz, it's got to be pretty close. This is stable down now, staying at, well, anyways, I'm just going to say 10 milliamps. So now I want to show you the finding I had. I showed this in the other video, but it didn't go all the way down to 10. Okay, now I take off. Now the shunt bar windings are free. They are not shorted out. Now, the amps input goes up to 40 or 50 milliamps, jumping back and forth. And the amps to cap, the output amps has gone up and the voltage has gone up, but the ratio of in and out has gone down. Okay, so here it is. Everything's free, okay? 50 milliamps. Now I short it out. I short out those shunt windings. Now it goes down to 2. And it'll go down to 1. So let's say 15 milliamps. Anyways, you see, it seems to really suck the back EMF through the shunt bars when I short out the windings. That's what I'm getting at. Okay, that's all I wanted to show. Thanks for watching.